Hi everybody, this is Ms. Frazita. We're looking at Chapter 4, Section 5 today. And even though the title of the section is Linearization and Newton's Method, we won't be covering Newton's Method. It's not covered on your AP exam. There's another topic actually, even though it's not in the title, which is differentials. And that is also not covered on your AP exam. So we're going to stick with just linearization and keep this short today. Okay, so what does it mean, linearization? So we've talked a lot in here about, find the equation of the line that's tangent to the curve at the point. So it goes along the same line, same thought line here. So it says a line that is tangent to the graph of f of x will look like f of x near the point of tangency. Hence, the tangent line will approximate the function there. Okay, so if we stop there for a second and just think about it, if you were to type in some sort of function into your graphing calculator and hit graph, and then you take a particular point of tangency, okay, or the center of approximation, and you were to zoom in with your graphing calculator, zoom in, blow it up on that point, zoom in again, and zoom in again. So eventually your curve is going to start flattening out as you zoom in closer and closer. It just looks more and more linear. So the idea is that if you take a line that's tangent to your curve, that line that's actually tangent to it is a pretty good approximation for the function itself at that point. So if you look at an equation of a line, equation of a line is always just first degree. That's what a line is. So it's a pretty simple equation, whereas your actual function might be like a third degree polynomial or something, not nearly as simple as just the line, or it could even be worse, right? So the idea is that if you're trying to approximate something about your curve, you can get an approximation by looking at the line that's tangent to the curve instead of looking at the curve itself. So if, for example, my goal is to figure out the y-coordinate of my function when x is 3, or 3.1, let's say, then I can draw a line that's tangent to the graph, let's say at 3, and I can use the equation of the line to approximate what the y-coordinate is at 3.3, rather than using the function itself, trying to figure out the height at 3.3. Okay, so if I go ahead and drop down here, there is a formula for the linearization, but I have to tell you, it's really not a formula. It's just the point-slope form of a line. So this linearization thing is really just coming up with the equation of the line, which we have done many times in here before. So looking at my point-slope form, we always plug in a point x1, y1. Well, we're going to picture our point of tangency, or our center of approximation here, as some point a, f of a. So my x1 is a, and my y1 is f of a. And then, as we've seen multiple times, our slope, what we're going to use is the derivative at that point of tangency. So we would use f prime of our point of tangency, a. So this right here is basically our linearization equation, which, again, it's just a point-slope form of a line, so don't make it more complicated than that. I believe the book will move the f of a term to the right side of the equation to get the y by itself, and then they, instead of calling it y, they call it L of x for linearization. But again, I don't even think it's necessary to move things around. You can just write it out like a point-slope equation with your a, f of a, and f prime of a plugged in. So when we're using our linearization, again, we're always looking at values that are close to the point of tangency. So I wouldn't want to use this equation of my line that's tangent if I'm trying to approximate a value for my function that's really far from my point of tangency. So my line does a good job approximating my function for values that are close to the point of tangency. Okay, so be careful. And this actually should sound kind of familiar with the approximating idea. Let me read at the bottom there. It says we can use linearization of f of x if we only care about the values near our point of tangency and prefer a simpler equation. And I put in here just, to kind of flash back to in behavior model. To me, it kind of rang a bell, because if you think about in behavior model, we use the in behavior model to approximate a more complicated function. So I thought, what the heck, why not? Let's just review in behavior model because your AP exam is only a few months away. Okay, it's several months away. Anyway, so if I look at this rational function, our in behavior model was basically just the highest power of x on top and the highest power of x on bottom. Those two terms reduced down gave us 1/5 of x to the 2. So this is a nice, simple looking little parabola opening up. So that tells me that this original function, even though it looks kind of big and scary, I know that it will look the same as this parabola for really big values of x and really small values of x. Now right around the center of the graph near the origin, totally looks different. It won't be a parabola. However, I know it's going to go up to the right and up to the left. So as x goes to infinity, y will go to infinity. And when x goes to minus infinity, y will go to positive infinity. So again, that's just a quick review in behavior model. Okay. Back to our linearization now. So if I give you an example question, here's my function, and it asks you find the linearization at x equals -4. That means they want the equation, and I want to know by point of tangency, or the center of approximation, is -4. So first of all, if I'm going to be using my point slope form of a line, if I want to think of it that way, I need the point xy and I need the slope at that point. So they only gave me the x coordinate. I need to plug in the x coordinate into my function to get the y. So I did that, came out 5. So I have the point -4, 5. Great. Now I need the slope at the point when x is -4. So I took the derivative and I plugged in -4. Can follow my calculation, and it came out -4/5. Really, I'm done. This is no different than find the equation of a line tangent to the curve at the point. It's exactly the same thing. So I would have y minus 5 equals my slope, -4/5 times x minus 4. That's it. That's all there is to it. Now, if you want to use the fancy new notation, here's your equation. And again, your y coordinate was the 5, so f of -4 was 5. Your slope was f prime of -4, came out -4/5. And then the x coordinate when a is -4. So here's my final answer for my linearization equation. So the question is, how accurate is L of -4 plus 0.1? So again, our point of tangency is -4, and the whole concept of linearization is that this line is a lot friendlier to use than the original function to approximate values of y near our point of tangency. So if I'm looking at -4 plus 0.1 and I plug that into my equation that I just got, my L of x equation, my y coordinate comes out 5.08. Now the question is, how accurate is it? So if I go back up to my original function and I go ahead and plug in -4.1 squared plus 9 square root, I get 5.0804 something, right? So the difference, very small. So my linearization approximation was pretty darn good. My difference was off by 0.004, 0004. Okay, so again, the value that I was using, I was using -4 to approximate a number very close to -4, and that's why why my linearization equation did a good job. If I wanted to add or subtract 2, well, that's not very close to my point of tangency, and chances are my approximation is going to get pretty bad. Okay, so that is it. I hope you understood that. I will see you guys soon. Thank you.